Yeah, there we go. Okay.
I guess for me, it's just lower some of these hybridization problems.
Okay.
In the last 2 weeks.
Oh, yeah. Okay. You know what I need to do? I need to identify what this is, because when we have the PowerPoints up here, it's easy to tell which one it is. But we're just doing a review. 213 spray. And this is exam 9 or 7. Check. Exam 7. Chapter 9.4 through 9.8. Round.
You know,
Hmm?
about the platform, I think my research paper board, my English final research paper.
Oh, is it going to be easier after doing this?
This will be, no, I'll have to focus on a lab report now.
Oh, I see. Yes.
It's due Wednesday.
Yeah. Dividing your attentions can be a, yeah. Okay. And this is a review. Here we go. Okay. So let's see, where do we run into hybridization? Number 1. Do you have one in particular? Or do you want to do that?
I just have the last 2. I don't care which 2 yet. I just told you those last 2.
Okay. Well, let's try to get the ball rolling. We'll just take number 1. Okay, for number 1, atoms that are Sp2 hybridized. Sp2 hybridized. Hybridized. Form how many pi bonds? Well, the question is to say, what does Sp2 hybridization mean? If we have Sp2 means there are 3 hybrid orbitals. So we're going to have something in the middle, and then we're going to have trigonal planar. I think 1, 2, 3. So what does that leave us? That leaves us with an unused p orbital, unhybridized p orbital. Right? So those p orbitals will overlap and form a pi bond, because these are all sigmas. So you have an unused p orbital that can overlap. So that's why the answer given is B, or 1 pi orbital. Right. If we didn't use that for something, for this bond, then we would have Sp3 hybridization. Okay. Let's look. Oh, okay. Let's look at 3. So we've got a molecule that's like that, that, that. Here we go. And these carbons are numbered. 1, 2, 3, 4. What's the hybridization of atoms atoms here? This one, and this one. Okay. So what we need to do is say, how many electron pairs do we have? So if we say oxygen has how many? It has 6, right? So if it has 6 electrons, it's used 1 over here and 1 over there for that bond, for those 2 bonds. So that means we've only used 2 of them. So we have 4 electrons left. That means that we have a pair there and a pair there. Right? So we've got 1, 2, 3, 4. We've got 4 groups. And 4 groups means tetrahedral. And tetrahedral means Sp3, because you have to have 4 hybridized orbitals. Okay. This one is simple. It's got 1, 2, 3, 4. So it's also Sp3. This one has 1, 2. So it only needs 2 Sp. And this one has 3. So it's Sp2. Okay. So let's see if that's A is Sp3, Sp3, Sp, Sp2. Yep. Okay. At 11? Okay. 11. Use the molecules below to answer the next 3 questions. Next 3 questions? There's only 1 question. Okay, I need to correct that. The next question. Okay. I think what I did was I pulled that out of a question set, and it actually had this assigned to 3 questions, but I only used 1 of them. Okay, so we've got this molecule. This is number 11. We've got this one. Which is C6H6. In organic chemistry, when we write a molecule like that, each one of these apexes is a carbon atom. And then we don't write the hydrogen atoms in. So you look for 4 bonds. Right? We've got 1, 2, 3 bonds to that carbon. That means it only has room for 1 hydrogen. That's why 6 hydrogens. We've got 6 carbons, and then each one has a hydrogen. That's why. Okay, so this one, these are all cyclical compounds like that, like that. This one's C6H8, because these can have 2 hydrogens. And then the last one is that C6H10. Okay. Which molecules have at least 1 carbon atom that is sp hybridized? Okay, so knowing what we know, each one of these has a hydrogen on it. That one has 1, 2, 3, 4. This has 2. This has 2. This has 2, 2, 1, 2, 3, 4. There, 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 there. 2, 4, 6, 8, 10. Okay. So ask yourself, what type of hybridization is required for 1, 2, 3 groups? Sp2, right? And that's for the all the way around. This one is Sp2 here. That one's Sp2. That one's sp2, sp2. This one is sp3. And this one's sp3 because it has 1, 2, 3, 4. And similarly, this one has 4, 4, 4, 4. So all of these are sp3, and these two are sp2. So how many have SPs? None. Oh, okay. Yeah. I understand. Nobody has. So that should throw everybody. If we needed an SP hybrid, how would we get it? We need a linear, don't we? Like just two groups. So how do we get two groups assigned to a carbon? Well, one way is to bond it to another carbon. Like that. Then we have two groups here, and that's sp hybridized. You can't get an sp hybrid with a cyclic compound. It's impossible. You can't fit 3 bonds. Let's see, can you? 1, 2, 3? No, because if you put 3 bonds in here to this one, one there, 3 bonds in there. Oh, maybe so. I can't imagine. No, you can't. The strain would be too much, right? If we put 3 bonds here, then it would have to be linear on both sides. It would have to pull that one out here, pull this one up here to make it linear. And that structure will not stand it. So cyclic structures like this with carbon, you'll never get an sp hybrid. Okay, are there any others in there with organic mess? Number 24 could be a problem. Oh, okay, you want to back up? Number 8. Yes, they start. Okay, so we're starting from this drawing, 8. And we're doing that. And we're doing this, 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 with a carbon at each one. And then we're doing a nitrogen. That's the skeleton. How many of the atoms are sp2 hybridized? If those are the tetracyanoethylene, let me check the because that's beyond this class. I don't know why. Let me see. Does this appear on the exam? If it doesn't, then you waste your time. No, I left it off. Yeah. To answer this question, you need to know what the name means. Cyano is this. Right? So tetracyano would be that. And then that has an octet. This one's going to have lone pairs out here where it's octet. And then there are no hydrogens in here. Right? This is everything. So in order to have an octet for these 2 carbons, the best way to do it is to put a double bond in the middle. Then you got 8, 8, 8, 8, 8, 8. So the question to that one is sp2 hybridized means 3 groups. 1, 2, 3. This one is sp2 and this one's sp2. So there are 2 sp2 hybridized. But I left it off the exam. This must have happened before, and I just managed to create an exam without that one there. That's not hardly fair, is it? Okay, so let's see. Do we want to go to the back and be sure we cover those that are bugging? What is that page? Is that 57? No, 59 and 60?
Yeah, that's what
Okay.
he said today he wants to do.
Okay. Just lead up to it. Okay, 57. Give the bond order for each of the following. Okay, so we got A, B, C, D, E, and F. This one is dihydrogen. This one is that one. This one is that one. Then we have cyanide ion, cyanide molecule, cyanide cation. Okay, let me see. This is a fair question. That looks kind of difficult. My explanation works. Okay. So let's take them in groups. Right? If we're going to draw the molecular orbitals, when it asks for bond order, you have to go to molecular orbitals to do that. So we've got a hydrogen on this side, hydrogen on that side, and we've got a 1s here and a 1s there, each with one electron in it. And here's our energy scale. Right? So this one's going to form 2. Right? Starts with 2, has to end with 2. This is going to be a sigma from the 1s, and this is going to be a sigma star from the 1s. Okay? So we're going to fill the orbitals. We're going to take these 2 electrons, and they go right there. Okay? So for H2, the bond order is going to be 2 minus 0 divided by 2 equals 1. Okay? And we can use the same arrangement for that one. So this one is going to be a positive ion. We have to lose 1 electron. Right? So if we lose 1 electron here, doesn't matter which one it comes from. Then we're going to have 1 minus 0 divided by 2, which is 1/2. Okay? If we have a negative ion that we've added an electron, it has to go into that one because this one's full. So this one is 2 minus 1 over 2, and that's 1/2. Okay? So that was the easy one. That's hydrogen. Now for the cyano. Let's see. Cyano. For cyano, we've got, let's see, is this CN? That's probably got mixing. Yeah, the cyano's got mixing. Does it give you that clue? Doesn't give you the clue. Okay. So carbon, nitrogen. And the valence for carbon is going to be 2s, 2p. So we've got a 2s. We've got 2p, 3 of them, 1 of them here. Nitrogen is also going to have 2s, 2p. probably down here somewhere. Okay. Then we combine. This is going to be a sigma from a 2s. This is going to be a sigma star from a 2s. And then we're going to form 6 here. So we're going to have sigma and sigma star from a 2p. Oops. And then we're going to have 2 of these and 2 of those. No, they're inverted. Okay, that's right, because there's mixing. I'm sorry. Since there's mixing, this sigma goes in here, and these go in here. So these are pi 2p's. This is pi star 2p. Now, if you look at this cheat sheet at the back, here we go. Both carbon and nitrogen are in this part. So that means, this is easier to understand. That means that pi is below the sigma. That means there's mixing. Here there's no mixing. No mixing means the pi and the pi star in the middle, and the sigma star on the outside. But when there's mixing, pi comes below the sigma. Since they're both these monodiatomics are experience mixing, then carbon and nitrogen together have to be mixed. So that's why we put this one down here rather than that one down here. So now we go in and say carbon has these 2 and these 2. Has 4. And nitrogen has these 2 and there's 3, because nitrogen has 5. Okay. Now we can take 2, 4, 6, 8, 9, and put our 9 electrons in. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's this one, right? Okay, because we use neutral amounts for each one. So that means the bond order is going to be 2, 4, 6, 7 minus 2. 7 minus 2 divided by 2 equals 2.5. Okay. If we add 1, where does it go? See, these are full, these are full, these are full. It has to go in here. There. So that gives us 8. 2, 4. I did that wrong. I'm sorry. 2, 4, 6, 7. Oh, that was right. 7 minus 2. Sorry, I don't know what I was thinking of. That was right. 2.5. Then if we add 1, it's 2, 4, 6, 8. Add 1 here. Minus 2 over 2, which is 3. You see, before that one was missing. And then I added it, so it's 2, 4, 6, 8. We added 1 here. Minus 2, this is the only anti-bonding there is. So that's 6 divided by 2 is 3. Then if we take away one from there, that means both of these are gone. Right? So now we have 2, 4, 6 minus 2 divided by 2 equals 2. I think that's the right answer. Yeah. That was a difficult one. The key to this one, well, this one's easy, but the key to this one is understanding that these are mixed. So that changes the order and puts the pi bonding below the sigma bonding. Okay, that was 57. 57. 58. Let's look at 58. Okay. 58 says, consider the structure of glycine. This is the simplest amino acids. You know what amino acids are? Amino acids are the building blocks for proteins. You hook a bunch of amino acids together, you get a protein. Yeah. So this is the simplest amino acid. I'm going to draw it like they drew it here. There. There. This is carbon 1, carbon 2. So let's move that out of the way. This is carbon 2. And then there's the amino part. There's the acid part. Amino acid. Okay. Indicate the hybridization at each nitrogen and carbon atom in the molecule. Okay. So we got 2 carbons and 1 nitrogen. So the hybridization here is 1, 2, 3 groups. Sp2. 1, 2, 3, 4 groups. Sp3. Now the key to this one is, how many electrons do we have for nitrogen? If we look at nitrogen, it has 5 valence electrons. Right? One of them's used here. 2 of them are used here for those hydrogens. That leaves 2 more. So we got a lone pair. That's the trick. So now we have 1, 2, 3, 4. This is sp3. Okay. Then what is the total number of bonds in the molecule? Okay. Total number of bonds. We've got 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 total bonds. How many pi bonds? Only 1. And that doubles. I'm sorry? Oh, yeah, take your time. Yeah. Okay. 59. Okay, explain the concept of delocalization of electrons in sulfur trioxide. Indicate how this idea relates to resonance. I'm not sure. It was part of this last discussion with pi systems. There it is. There's a slide for delocalization. When you have a, let's just use carbon. When you have a sigma bond, those electrons are localized, right? They can't move. They're between those carbons, that's it. When you have a system that has other carbons, and you've got these p orbitals that can overlap, but they're also associated with other carbons with their own. So what happens is you can get a general overlapping of all of these p orbitals in that ring. And that delocalizes the electrons that might be here. They're actually smeared over the entire, that's delocalization. And delocalization is a stabilizing force. If they've got more room to move around, they're happier. Okay, back to 59. We need to understand the dot structure for sulfur trioxide. So let's do that first. Sulfur is 6, oxygen 6, so it's 4 times 6 is 24. Okay, so we've got a sulfur, 3 oxygens, so that's 2, 4, 6 is 18. So we got 2, 4, 6, 8, 10, 12, 14, 16, 8, 2, 4, 6, 8. 6, 8 times 3 is 24. Okay. So now we need to give sulfur an octet. So we could do this, or we could do this, or we could do this. So we got 3 possibilities. So what we're going to have is resonance. Right? Let's do it this way. And then it's like this one. That. Just like this one. Actually, these should be trigonal planar. Right. So if I'm going to be more accurate, I should say that, and then that. And then this one would be that, that. And this one would be that. And that. There we go. There we go. So those are our possible Lewis dot structures with resonance. So our focus now is on delocalization. Because we know that can't be. With the localized electron model, this is the only way to represent them, because the electrons have to be assigned to individual atoms or inside a bond. So delocalization allows us to smear these electrons over the entire molecule. Right? So if we wrote one structure for this entire thing, we would say this is a more accurate representation. These are partial double bonds. Right? And the electrons get smeared over the entire thing. Let's see, how would I say that? One pair of electrons, one of these lone pairs from an oxygen, actually the picture explains it better than words. I mean, I've got words here, but what we're saying is, by representing each of these three structures, or by this structure, either one is valid. We're saying that the double bond character is smeared over the whole molecule, or those pi electrons that are part of that double bond. That's a pi. It's a sigma. Those pi electrons are delocalized over the entire molecule. And that's really a logical extension of resonance. Resonance is required with the localized electron model. But once we start talking about not hybrid orbitals, but molecular orbitals, then we can move those electrons all over the molecule. Molecular orbitals are characteristics of that one molecule and no other. $60. You get? Yeah. Okay. Okay. Come on. Behave yourself. Stick you in my pocket. 60. That thing's starting to wear out. Let me get see if this purple works. Okay. So we've got these three molecules, and we want to fill in this table. Let me construct the table first. So we want molecular, it says structure, geometry is a better word, I think. Means the same thing in this case. What type of hybridization does it have? Bond angles. And an example. Okay. So this is molecule A, B, and C. Now, does the text give us any guidelines? Molecule A has a hybridization of Sp3. That's given. Okay. So let me change colors for the stuff that's not given. The blue, or sort of the purple. Okay. Sp3. What can we say about this one? If it's Sp3, the molecular geometry is tetrahedral. Actually, that's not true either. The electronic geometry is tetrahedral. It's only molecular geometry if all of these four orbitals are occupied by bonds. So that needs some correction. tetrahedral. So what are the bond angles? Well, for tetrahedral, the standard value is 109.5. And the best example of that one, if we're going to say tetrahedral molecular, then we have to say something like this. Methane. Or carbon tetrachloride that would work too. Now, more information we're given. Molecule B has 2 more effective pairs, electron pairs around the central atom than molecule A. 2 more pairs. Okay. So if we've got 2 more pairs, where are they going to go? They're already used up, right? So we need D2, Sp3. So that means octahedral. And the bond angles there, I always have to draw my structure. We've got one up here and one down here. Right, so we do like that, that. Yeah. Okay. So we got our central atom and then the peripherals. So what are the bond angles? Well, these bond angles are 90 degrees. Here, here, here. These bond angles are 180. Go from here to here. So we've got 2 bond angles. Most of them are 90 degrees. But we've got one here. Because the bond angle specifies that the central angle is at the, what do they call it? You do an angle like that. The fulcrum. Not the fulcrum. I forget the word. But the angle is 90 degrees or 180 degrees. So an example, well, you need 6 atoms scattered around here. And this one works. Sulfur hexafluoride. C consists of 1 sigma bond and 2 pi bonds. Okay, if it's got 1 sigma and 2 pi's, where do the pi's come from? The pi's come from unused p orbitals, right? So we can only use 1 p orbital for hybridization and 1 sigma for hybridization. So that means it has to be Sp hybridized, right? Because we need these extra p orbitals reserved for our pi bonds. So Sp hybridization is linear. And the only possible angle is 180 degrees. And example, carbon monoxide, or acetylene, or cyanide ion, any one of those, as long as they have 2 pi bonds. Okay. 61. Did that get you in trouble?
I didn't notice it. 60.
61 makes use of the cheat sheets, where it actually gives you the molecular orbital structure. All right, let's just do 61. Okay. Draw a molecular orbital diagram for O2 and N2 using molecular orbital theory. Explain why the removal of 1 electron in oxygen strengthens the bond, while the removal of 1 electron in nitrogen weakens the bond. Okay. So, oxygen and nitrogen. So O2, N2, here. Since I gave you, where is it? Here it is. Since I gave you the structures here, you know, you don't have to fret over, and that's going to be on the exam. So you just take the, draw the structure. You can do it. You can do it like, actually, it's requested here that you fill in the actual structure. So for O2, we have one down here. That's sigma from the 2s. And then we have sigma star from the 2s. Then oxygen. Oxygen is no mixing. So the next one is going to be sigma from the 2p. Then we're going to have pi's from the 2p's. Then we're going to have pi stars from the 2p's. Then we're going to have the sigma stars from the 2p's. So this sigma, that sigma star, and then the pi's in the middle. Okay, so oxygen. How many do we have? 6. 12 electrons total, right? So we just start filling them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Go. Now let's do nitrogen. Nitrogen experiences sp mixing. So the order changes. So we've got sigma from the 2s, and we have sigma star from the 2s. But then, rather than sigma from the 2p, we have pi's from the 2p. Then we have sigma from the 2p. Then we have then we have pi stars from the 2p. Then we have sigma stars from the 2p. Okay. So got this one. There we go. 1, 2, 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4, 5, 6, 7. Okay, we're good. Now, electrons. Nitrogen is 5 each. So we're going to have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. What's the bond order as is? 2, 4, 6, 8. Eight minus 2, 3, 4. Divided by 2 equals 2 for oxygen. See if I got that right. 2, 4, 6, 8. 2, 4. Yep. Okay, bond order for nitrogen as is. This is before we do what it tells us to. So this is 2, 4, 6, 8. Minus 1, 2, right? Divided by 2. So that's 6 divided by 2 is 3. Okay. So as is, the nitrogen molecules should be more strongly bound than the dioxygen molecule. Lose something? Okay, so what happens if we remove an electron from each one? So if we remove an electron from this one, it comes from a star orbital, doesn't it? So that means the bond order of, let's see, remove one electron makes it positive. So the bond order for the positive one is going to be 8 minus 3 divided by 2. So that's 5 divided by 2.5. So that strengthens the oxygen molecule because you're removing an electron from a star orbital, an antibonding orbital. When you remove one from nitrogen, you're removing it from a bonding orbital. So now this one is going to be 7 minus 2 divided by 3, which is 2.5. So now you remove, let's see. Yeah. Now they're both the same bond order if we move an electron. But the process weakens the N2 and strengthens the O2. Right? Strengthens that one, weakens this one. So it all depends. The explanation for that is, where does that electron come from? The oxygen, it comes from an antibonding orbital. Nitrogen, it comes from bonding orbital. Weakens nitrogen, strengthens oxygen. Okay? Wait, quick. Huh? Oh, paramagnetism and diamagnetism? Yeah. Uh-huh. Oh, let me see. If I have a review problem in there for it, I should have. Take me a second, just. Let's see. It might be easier to find it if I look in the word problems.
I mean, 56
Oh, yeah. Yeah, that one talks about it. We can do that. Three, 6, 9, they're 9. No problem. Okay. The best way to do this one is, rather than draw the complete diagram, is to use the shorthand notation. Okay. Kind of like when we were doing electronic structures, we use a shorthand notation for the molecular orbital structures too. You know, that was crapping out on me. See if the black is back in business. Okay. So we've got okay. This one is O2, this one is O2 minus, this one's diboron, dicarbon. Did I skip one? Yes. Oh, 2 minus. Yeah. Thank you. O2. D is diboron. Have carbon. F is N2, F2, Cn minus P. Okay. So, the best way to do this one is to find, particularly for those where we're going to add or subtract electrons, to find this will start with this one and these two will follow. But what you need is the is that cheat sheet at the back. Because that'll take any guesswork out of whether or not there's mixing. Here we go. So rather than draw the stacked orbitals, we're going to lay them out like this. And for oxygen, we have, let's see, do I go all the way out there? Yeah, I do. Okay, so the order here, and we're only going to use the valence orbitals. Right, so that's second period. Second period. We're just going to leave the 1s's out. They don't matter anyway, not in this case. So this one's sigma from a 2s, then we have sigma star from a 2s, and then we have sigma from a 2p, and a pi from a 2p, pi star from a 2p. And then if we needed it, we would sigma star. So that's the shorthand version. And this shows that there's no mixing because both of the pi's are between the sigmas, or originating from p's. Now, how many electrons do we have? 2 times 6 is 12, right? Okay. Every sigma can have 2. So there's 2, 4, 6, and then every pi can have 2 pi's. So these can have 4 each. 2, 4, 6, 8, 10, 12. Right? And we don't need this one. All right. So, does that make oxygen paramagnetic or dimagnetic? Paramagnetic means that you have at least one unpaired electron. So where do we have it? That one's full, that one's full, that one's full, that one's full. That means they're all paired. But this one has 2 orbitals and 1 each. So those are unpaired. That means this oxygen is paramagnetic. Okay? If we add an electron, where is it going? It's going out here, right? So this has 3. Well, that means that we've got that paired, but we still have an unpaired. So it's also paramagnetic. Now, if we add 2 electrons, there are no pairs. So it's dimagnetic. Okay. Now, boron. So boron, we'll go back over here. Look up boron. Boron is going to have mixing. So we've got sigma 2s, sigma star 2s. Then we're going to put that pi down here. first, 2p. Then we're going to have sigma, 2p. Then we're going to have star, 2p. Okay, how many boron? 3 each, so we have 6. Okay, we're not going to need those anyway. So we got 2 here, and 2 there. Okay, so we know that these 2 are going to be unpaired. So this is paramagnetic. Okay, carbon. Carbon has mixing. 2s star 2s pi 2p, then carbon 2p, sigma 2p. Let's see if that's enough. Each carbon is going to have 4, so that's 8, 2, 4, 6, 8. Okay, so we didn't need that. So these are all going to be paired. This is diamagnetic. Huh? Nitrogen should be diamagnetic, fluorine diamagnetic, Cn. We did that one earlier, Cn minus. Where? Where's that? Oh, that's a mistake. Yeah, that's a typo. 56. Let me make a note in case. Okay, so it's not in this version. That's my key. So let me look at the review. 6. See if it shows it for me. Yep, there it is.
I noticed that.
Unprepared.
Yeah.
Yep. No problem there. Yeah, just on that copy. Let's see. Phosphorus would be like nitrogen. Yeah, phosphorus would be like nitrogen, only this one has second period, and this one has third period. But they fill the same way, because it's 5 and 5, or 10 and 10s. Yeah. Yeah. But the rest of them are diamagnetic. These are the only pairs. That one, that one. Oh, yeah. If yeah,
It's weird.
if I were to put that one on a test, I'd probably give you a point for each one and say identify paramagnetic. And I probably wouldn't put that in here.
It's silly.
Okay. Yeah, just understanding how to do it. Once you got the method down, just busy work. Okay. All right. Let's see.
I don't know.
No? Okay. Let me do a quick run through and see if anything else pops out at me. Mm-hmm. Yep. I think we got all our bases covered here. So let's put this one. Put that one right there.
So for the pages that we don't use in this, we just don't use the line, right?
Oh, yeah, it's big one. There's always going to be too much space in there.
Yeah, that is better.
Yep.
So for the graphs, you'll be any graphs for any type like this on the left side, right?
Uh-huh.
Okay.
That's the best place to put it.
Yeah. I was making sure. I think the one that has that. I just did that.
Okay, there's your copies. There.
This is one faster than the first one.
Really?
Yeah.
Were you busier this semester?
Less.
Less busy?
Yeah.
Oh.
I feel like I've hard classes this semester, but last semester I had more classes.
But they were easier.
Yeah.
Oh. Yeah.
At least it's only that they like that.
Which math do you take?
That's
Algebra? Or have you already had it?
I did that last semester of college algebra.
Well, this trig? Trig? Trig and pre-calc?
Maybe.
Yeah. That sounds like the sequence.
I think
Now, what degree are you trying to
I've already switched my major. Now it's in geography. After this class, I have this class still and everything now, but for this I go to statistics,
Oh, okay.
which I didn't get to take this semester to fill up quicker than I thought.
Yeah.
But I had that in high school, although I'm not going to do the exact same thing, but I can.
It's really similar.
Yeah.
Probably in more depth.
Yeah, I actually like it.
Oh, yeah, I love statistics.
I like that.
Yeah.
Because after like the first few chapters, once I understood, I just get better and better and better.
Yeah.
It's like you read, I'm still like, yeah, you heard a lot of them.
My second statistics course was more fun. I had an animal scientist teaching. The version I took was called experimental statistics.
I don't have one that calculus, because I don't take that calculus.
Right. Yeah, I didn't go for a calculus version either. That seemed like overkill to me.
Do what?
It's weird that I'm the only one